today we are going to do two topics. Number one, the physical properties of phenol. So we are going to discuss physical properties of phenol. The first property we can discuss is regarding its solubility. Phenol is a organic compound, so it dissolves in organic solvents like ether, alcohol, etc. But phenols are also sparingly soluble. Sparingly means less soluble. Sparingly soluble in water. Apart from dissolving in organic solvents like ether and alcohol, it is sparingly soluble in water. It is attracted towards water, but the solubility is less. It is sparingly soluble in water. First of all, why it is attracted towards water? Why does it dissolve in water? The simple reason: phenol will be able to form hydrogen bonding with water. Phenol will be able to form hydrogen bonding with water. OH bond, is polar. Electron goes towards oxygen because oxygen is more electronegative than hydrogen. Small negative charge, small positive charge. So when you put it in water, it will be attracted by water. Water is also a polar solvent. Electron goes towards oxygen with a negative charge over here and a positive charge over here, and they are attracting each other because of the formation of hydrogen bonding. What is this bonding called? Intermolecular hydrogen bonding. So phenol is attracted towards water due to the formation of intermolecular hydrogen bonding. But you can see phenol has got such a big phenyl group, or the benzene ring, which is non-polar or water heating, that is hydrophobic. So because phenol has got such a huge water heating part, the benzene ring, its solubility in the water will be very, very less. It is sparingly soluble in water. So the first point is that phenol is sparingly soluble or less soluble in water. It is soluble in water due to the formation of intermolecular hydrogen bonding with water, but its solubility in the water is very less because of the presence of big non-polar phenyl group, the hydrophobic group, that is the hydrocarbon part, which repels water. And as I told you, phenol, since it is an organic compound, it is also in the organic solvents like ether and alcohol. So phenol is basically sparingly soluble in water. It has been found that phenol dissolves readily in dilute NaOH. Phenol is readily soluble in dilute NaOH. Phenol readily soluble in dilute NaOH. Let's investigate why it is readily soluble in dilute NaOH. Dilute NaOH means NaOH plus water. The phenol is going to dissolve in dilute NaOH because of its peculiar property, which we are going to discuss today itself. Phenol has got acidic nature. It is much more acidic as compared to alcohol. If you remember, alcohol do not turn blue litmus red, but phenol dilute solution do turn blue litmus red. It's more acidic than alcohol. We'll prove it later on also. So when you put phenol in dilute NaOH, that is, you put in NaOH and water. Phenol being an acidic compound, it reacts with the base NaOH. It forms a salt. It will form a salt, sodium phenoxide. It forms a salt called sodium phenoxide plus water. And sodium phenoxide is a water soluble salt. Water soluble salt. This salt is going to dissolve in water. You know what is the condition for the salt to dissolve in water? You've done in 11th class. The hydration energy should be more than the lattice energy. So its hydration energy is more than lattice energy. It dissolves in water. So phenol dissolves readily in dilute NaOH because of its acidic nature. If you mix phenol, NaOH and water, phenol being an acidic compound, it reacts with NaOH, which is a base to form a salt, sodium phenoxide. and sodium phenoxide will readily dissolve in water. So phenol is sparingly soluble in water due to the formation of hydrogen bonding with water. Its less solubility is attributed to the fact that it has a big non-polar hydrophobic phenyl group, but definitely it dissolves readily in dilute NaOH. It dissolves readily in dilute NaOH. Now we are going to compare the second property of phenol, that is the boiling point. Phenol boiling point is more than corresponding aromatic hydrocarbon. Like phenol boiling point will be higher than the hydrocarbon, that is toluene. You know what is toluene? Benzene with CH3. It will be even higher than aryl halides, like it will be higher than chlorobenzene, bromobenzene and iodobenzene. So let's investigate why boiling point of phenol is higher than corresponding aromatic hydrocarbon and even higher than aryl halide. Boiling point depends directly on intermolecular force of attraction. That is force of attraction between the molecule. Intermolecular force of attraction. More is intermolecular force of attraction, more will be the boiling point. So between the phenol molecules, let's see what type of intermolecular force of attraction is there. Between phenol molecule, the intermolecular force of attraction which is there is strong intermolecular hydrogen. This is one phenol, this is negative, this is positive, this is another phenol. OH bond you know is polar, this is negative, this is positive. So they will have a hydrogen bond. So intermolecular hydrogen bonding is present between the phenol molecules, and that's why phenol boiling point is more than that of toluene. It is higher than even as compared to the chlorobenzene. So phenol has got a higher boiling point because of the presence of strong intermolecular hydrogen bonding. Now let us do one question which already we have done 11th class, but we can discuss over here also. We will compare the boiling point of two compounds. Like we are going to compare the boiling point of para-nitrophenol. This is what is para-nitrophenol with ortho-nitrophenol. Let's find out which has got higher boiling point and which has got the lower boiling point. Remember, on what factor the boiling point depends? It depends on intermolecular force of attraction. This is your para-nitrophenol. This is para-nitrophenol. And this is ortho-nitrophenol. So let's find out what is the force of attraction between the para-nitrophenol molecule and ortho-nitrophenol molecule. The one which has got higher intermolecular force of attraction will have the higher boiling point. So suppose we have got one more para-nitrophenol molecule, like this. This will be negative end, this will be the positive end. Again, this will be the positive end, this will be the negative end due to the electron difference, and they will attract each other. So again, the para-nitrophenol molecules, they are attracted by the formation of intermolecular hydrogen bond. Para-nitrophenol molecules have got intermolecular force of attraction, which is very, very strong. In the case of ortho-nitrophenol molecule, the two ortho-nitrophenol molecule will not be attracted by the hydrogen bond. Will not be attracted by the hydrogen bonding. Will not be attracted by the hydrogen bond. Any cases why? In para-nitrophenol molecule, what is there is that OH group and nitro group, they are very close. They are very close to each other. They are very close to each other. With the result, the OH group and this nitro group, they attract each other within the molecule. Similarly, this will also attract within the molecule. So with the result, between these two molecules, there is no intermolecular hydrogen bonding. Because the groups are not free, they are forming hydrogen bonding with each other. And within the molecule, the hydrogen bonding which takes place is called intramolecular hydrogen bonding. It has got intra, within the molecule, hydrogen bonding. So if we compare the boiling point of para-nitrophenol molecule and ortho-nitrophenol molecule, para-nitrophenol molecules have got higher boiling point as compared to ortho-nitrophenol molecule. Reason being, para-nitrophenol molecule, between the molecules, what type of force of attraction is there? Intermolecular hydrogen bonding. And between the ortho-nitrophenol molecule, there is no intermolecular hydrogen bonding, but ortho-nitrophenol molecule has got intramolecular hydrogen bonding. Intramolecular hydrogen bonding is there. So this has got a low boiling point, and this has got higher boiling point, and this has got the lower boiling point. This has got such a high boiling point that it is not steam volatile. Not steam volatile means if through para-nitrophenol molecule you pass steam, if through the para-nitrophenol molecule you pass steam, they will not vaporize. But this compound ortho-nitrophenol molecule has got low boiling point, so they are steam volatile. Steam volatile means if you pass through ortho-nitrophenol molecule, the molecule is going to change into the vapor phase. So this compound is not steam volatile, this compound is steam volatile. Why it is not steam volatile? It has higher boiling point. Why it has higher boiling point? Due to intermolecular hydrogen bonding. Why ortho-nitrophenol molecule is steam volatile? Because it has lower boiling point. Why it has got lower boiling point? Because of the presence of intramolecular hydrogen bonding. So suppose somebody asks you a question that you have a mixture of para as well as ortho-nitrophenol molecule. You got a mixture having both these molecules. How will you separate out? I think you would have guessed the answer. It's very simple. You've got a mixture of this and this. What you do? You pass steam. So if you pass steam having a mixture of these two molecules, along with the steam, who will vaporize or go into the vapor phase? This molecule. Who will remain behind? That is para-nitrophenol. So if you've got a mixture of ortho-nitrophenol and para-nitrophenol molecule, you can separate by a method called steam distillation. If you pass steam through the mixture of ortho-nitrophenol molecule and para-nitrophenol molecule, this will vaporize along with steam, come out with steam, and this will not come out with steam. So these were the two physical properties of phenol we have discussed right now. Number one, solubility, and number two is boiling point. This was slightly important, but this we have already discussed in 11th class. If you remember, there are two types of hydrogen bonding, intermolecular and intramolecular. Inter means between the two molecules, and intra means within the molecule. So this was as we go about the physical properties. Now we'll start with the chemical properties of phenol. Let us start with the chemical properties of phenol. Chemical properties of phenol. And today we'll be discussing only one chemical property of phenol. That is, as I've already told you, phenol is acidic in nature. Phenol is acidic in nature. So we'll reason out why phenol is acidic in nature. As I told you before also, phenol is so acidic, it does turn blue litmus red. It do turn blue litmus red. It is more acidic as compared to alcohol. Now phenol is acidic in nature because phenol has got the OH group. Phenol has the OH group. You know, oxygen and hydrogen, oxygen is more electronegative. So this is a negative end and this is a positive end. The bond, OH bond is polar. So bond can ionize. It will break like this and will give out H plus signs. So phenol is basically acidic in nature because it has a OH group which is polar. It can ionize to give out H plus signs. And it gives out, after giving out H plus, it changes into a conjugate base called phenoxide. It changes into a base called phenoxide ion. It changes into a base called phenoxide ion, a conjugate base. Phenoxide ion is a conjugate base of the phenol. You know what is a conjugate base? After an acid gives out H plus, the species which is formed is called as nothing but conjugate base. So we can write down phenol is acidic in nature. Phenol is acidic in nature as it has polar OH bond. It has polar OH bond which can ionize, to give H plus ion, and it forms phenoxide ion. After it gives out H plus, it forms phenoxide ion which is highly resonance stabilized. It gives out phenoxide ion which is having higher resonance stabilization. I'll just prove why it is having a high resonance stabilization. In fact, phenol is also resonance stabilized, but it is less resonance stabilized. I'll prove to you why this is less resonance stabilized. So phenol, which is less resonance stabilized, it will convert into phenoxide ion, which is having higher resonance stabilization. It has got a higher resonance stabilization, something very, very stable, higher resonance stabilization. So phenol, which is less stable, converts into something which is more stable, and when this becomes this, in a process it gives out H plus ions, and the one which gives out H plus ions is supposed to be nothing but having a nature that is acidic nature. So why phenol is acidic in nature? Because it gives out H plus ions to form something which is highly resonance stabilized, more resonance stabilized as compared to phenol. So now we have to reason out that why this is less stable and why that is more stable. So less stable thing becomes a more stable thing. In the process gives out H plus ions showing acidic nature. So let's prove why phenol is less resonance stabilized as compared to the phenoxide ion, which is more resonance stabilized. Let's find out why phenol resonating structures are less stable, whereas phenoxide ion resonating structures are more stable. So let us draw the resonating structure of phenol and phenoxide ion. These are the resonating structure of phenol, and these are the resonating structure of the ion called phenoxide ion. We are going to draw the resonating structure of phenol, and over here we are going to draw the resonating structure of phenoxide ion. Phenoxide ion is more resonance stabilized, phenol is less resonance stabilized. Let's prove it. If you draw the resonating structure of phenol, you will find the second structure, third structure and fourth structure, they are less stable, as I will go there. Now you know the rule, lone pair becomes a bond pair and bond pair becomes a lone pair. So that is the second structure. In the second structure you can see there is a positive charge separate and a negative charge separate. When positive and negative charge are separate, this is called charge separation. And any structure where there is a positive and negative separated out, like the second structure, positive and negative separate, they have got very high energy or less stability. So this structure has a very less stability. It has, we use the word charge separation. Negative and positive charges are separate. So we can go on further. Even third structure is very, very less stable, because you can see it also has a charge separation. It has a charge separation. Positive charges separate, negative charges separate. The word uses charge separation. So third structure is also very less stable. Even a fourth one will be very less stable. It also has a charge separation. So in most of the resonating structure of phenol, you can see they have a charge separation. The resonance stabilization is going to be less. The resonance stabilization is going to be less. Only in the first structure and the last structure we don't have any charge separation. Otherwise we have a charge separation. So why resonance is less resonance stabilized? Reason being, it's most of the resonating structure have the charge separation, so they are less stable. Now this is more stable, so definitely this will convert into something which is more stable. As we'll draw this resonating structure of phenoxide ion, you will find its resonating structure has no charge separation, because on oxygen there is already a negative charge. As the lone pair will go away, it will become neutral. You will see no positive charge on oxygen, no positive charge on oxygen, no charge separation. It is only the negative charge which is going to roam about or will get delocalized. see this structure doesn't have a charge separation. This structure will not have any charge separation, only negative charge getting delocalized. And we get with the original structure. So you can see in the resonating structure of phenoxadiene, we don't have any charge separation, only the negative charge is delocalized. So this molecule is less stable, this molecule is more stable. So this will readily convert into this, and as this readily converts into this, it gives out H plus ions. Anything which gives out H plus ions is supposed to be acidic in nature. So why phenol is acidic in nature? Because phenol gives out readily H plus ions to form something that is phenoxadiene, which is highly resonance stabilized. And why phenoxadiene resonating structure are highly resonance stabilized? Because there is no charge separation. There is a charge separation in the case of phenol. Now let me tell you, if suppose by putting some groups in this molecule, in the benzene ring, if I can make this thing more stable, this will be formed readily. I repeat, if I put some groups over here in the phenol molecule, in the benzene ring, and those groups make this compound even more stable, so this will convert more readily into this and will give out H plus ions more readily. So we are going to see which groups I should put in the phenol on the benzene ring, which will increase its acidic nature, which will increase the acidic nature of phenol. Which type of groups I should put in the phenol on the benzene ring, which will enhance its acidic nature, and which groups are going to decrease the acidic nature. Now it has been found that in phenol, if you put electron withdrawing groups, in phenol, if you put EWG, what is EWG stands for? Electron withdrawing groups, namely nitro group, namely halogen, namely CN group. So on benzene, in phenol, if you put electron withdrawing groups, NO2, X and Cn, it has been found all these groups are going to increase the acidic nature of phenol. If phenol molecule has got all these groups on benzene ring, NO2 group, halogen, you know, fluorine, chlorine, bromine, iodine and cyanide group, it will increase the acidic nature of phenol. Why it is so? Because if these groups are present in the benzene ring of the phenol, the corresponding phenoxadiene will become more stable. These groups make phenoxadiene more stable. So this will become readily into phenoxadiene, and the ability to give out H plus ions are going to increase. So if you put in phenol all these groups on benzene ring, the acidic nature will increase. And if you put in phenol on benzene ring the groups which are electron donating, if you're going to put a groups on benzene ring which are electron donating group, that is EDG, electron donating group, namely your R group, OR group, your NH2 group, all these are electron donating groups. If you put all these electron donating groups on the benzene ring in phenol, you will find the acidic nature will decrease. Acidic nature will decrease. So in phenol, if you put electron withdrawing group, acidic nature increases, and if you put electron donating group, the acidic nature of phenol is going to increase. Reason being, all these groups are going to increase the stability of phenoxadiene, and all these groups are going to decrease the stability of the phenoxide ion. Now let me show you the effect of all these groups. Now suppose if you got this molecule, this is called picric acid. This is called picric acid. This is called picric acid, 2,4,6 trinitrophenol. This is going to be very, very acidic. This is called picric acid. It is as strong acid as HCl or sulfuric acid, comparable to inorganic acid, because you can see it has got 3 electron withdrawing groups. It has 3 electron withdrawing groups. If you decrease electron withdrawing group over 1, let's say you put only 2 electron withdrawing group, you will find the acidic nature will decrease further. Remove one more, acidic nature will decrease further. Suppose we got orthonitrophenol. Remove even one, acidic nature will decrease. You have phenol. And if you decrease further, let's say you put a methoxy group at the para position, the acidic nature will be even lesser. Paramethoxyphenol will be even lesser acidic as compared to phenol, because OR group is a which group? Donating group. If you put all these groups on the benzene ring, the acidic nature of phenol will decrease. So phenol is acidic in nature. It turns blue litmus red. And in phenol, if you put electron withdrawing groups, meaning nitro group, cyanide group, and halogen group, acidic nature will increase. And if you put electron donating groups like R group, OR group, NH2 group, the acidic nature will decrease. Reason being, electron withdrawing group increases the stability of phenoxide ion, and electron donating group will decrease the stability of phenoxide ion. And definitely phenol is much more acidic as compared to alcohol. So this was the two things we have discussed in today's class. One was physical property, and the second one we have discussed was acidic nature of phenol. Thank you. Have a nice day.